I'm Steve Rowley. I'm one of the developers at Symbolics of a software product called Joshua. For the next few minutes, I'd like to show you a few examples of what Joshua can do for you as an engineer trying to develop a product that uses AI. I hope you'll come away convinced that Joshua is a pretty high-performance expert system development tool. We'll look at a couple of examples in the areas of hardware troubleshooting and weather prediction from databases. I hope to convince you with these examples that Joshua is not only high performance, but also very flexible in the way that it represents data, connects to other programs, and so on. It doesn't confine you to some shell language distinct from Lisp as many other products will. This kind of flexibility is as important as performance, if not more so, for applications that really get delivered. Solving the problem is only the first phase after all. You also have to deliver your solution in a package your customer will use. Now, successful AI applications are high leverage. One example of that is hardware troubleshooting, where you try to get a machine to diagnose failures in some piece of equipment. The problem with automated equipment, though, is that sometimes it works and sometimes it breaks. Worse, this sort of thing happens late at night or when the repairman's on vacation or when a new trainee repairman is available or just generally at the worst moment possible. For example, suppose you own a factory that's run by some sort of control computer. If that computer breaks, you just might end up paying $5,000 to $20,000 a minute for the privilege of owning that non-working factory. Anything that can speed up the process of getting things working again is worthwhile. Introducing an AI program to do the troubleshooting in cases like this has a number of advantages. It never gets tired, it never forgets a rule, and it never goes on vacation. Furthermore, if it does what's nowadays called model-based diagnosis, the program actually understands how the device is supposed to work and can explain its reasoning in those terms. Now, when have you ever gotten service that good from the person who works on your car? Here's an example circuit we're going to diagnose in Joshua. This is the silly but well-beloved standard example of AI troubleshooting literature. It's just a simple circuit of 3 multipliers and 2 adders that computes some polynomial of its inputs. You get to tell the program what you observe at the inputs and what you observe at the outputs of the circuit. Joshua will then use its understanding of how the circuit elements work in order to run a simulation of the circuit and look for conflicts with your observations. Then it will use the data dependencies, maintained by a truth maintenance system, to figure out what circuit elements are culprits who could account for these conflicts. This is what the user interface of the Joshua hardware troubleshooting program looks like. It was developed with the frame-up facility of the Symbolics system. Joshua lets you have full access to all the facilities of Genera. We see a display of the circuit we're diagnosing where the components are darkened according to how much we suspect they're broken. Right now, we believe everything is working, so they're all white. We also get to look at the various states of the troubleshooting engine. We get to see what the current set of conflicts between observation and simulation is, and we get an English description of the troubleshooter's line of reasoning. Let's give the troubleshooter some data that tells it the circuit is misbehaving and see what it does. Note that some observations have appeared at the inputs and outputs of the circuit. Now let's run a qualitative simulation of the circuit and find the conflicts. Note that the troubleshooter is now telling us what it's doing. First simulating, then looking for conflicts with observations. It's telling us here that it found a conflict between theory and observation at terminal F. Sure enough, terminal F is highlighted. We observed value 6, but we should have gotten 12, according to the simulation anyway. Now let's diagnose the circuit and see who the culprits are. The first culprit that could explain the failure at output F is adder 1, since it directly feeds output F. It contributes to this failure and is consistent, so Joshua marks it as a good candidate. The next possible culprit is multiplier 2, since it feeds output F as well. However, if multiplier 2 were broken, we'd see a bad value at the other output as well. Since we didn't observe such a failure, Joshua rejects multiplier 2 as a candidate. Thus, multiplier 2 is exonerated. The next candidate is multiplier 1, since it feeds output F as well. Joshua decides it's a good candidate. At this point, we've got 2 circuits that could explain the failure. We could just decide to replace both of them, or we could take an observation between them to try and decide which is broken. The point is that all this is automatic, and the program doing it can explain its reasoning. This is what's nowadays called model-based diagnosis. What it means is that Joshua has a principled understanding of how the circuit is supposed to work. The alternative is to try and understand all the ways it could not work, which is rather difficult. Nature is really clever at finding new and different ways to break things that you didn't think of beforehand. Let's take a look at how Joshua understands that circuit. The program is a mixture of forward and backward chaining rules. The forward rules simulate the circuit behavior. Here's an example. This is a forward chaining rule called adder forward. It says that if A is an adder, and it's known to be working, and you know the value at its A input, and you know the value at its B input, then you can compute the value at its sum output by adding. In other words, this just says adders add. More importantly, it says that every time we use this rule to deduce that an adder just added something, we should remember that depends on a bunch of other facts. In particular, it depends on the assumption that the adder is working. After all, non-working adders don't have to add. Maybe they emit smoke or something, but they're not required to add while doing so. Now let's talk about performance a bit. Joshua comes with a set of tools with which to measure program performance. Some are oriented toward general-purpose Lisp programs, while others are more tailored to Joshua programs. Now, the performance of the diagnosis you just saw is not too bad. It responded in more or less human timescales. Actually, it did the diagnosis much faster than I would have if I'd never seen the circuit before. I'd have had to take time to figure it out. Joshua was able to both figure out the proper behavior of the circuit and diagnose it tolerably quickly. The performance numbers came to something like 120 rules per second. That's not too bad, in fact comparable with almost all other expert system tools. However, we can do better. So far, we've seen Joshua used for writing a prototype quickly. Now, when it comes time to deliver our application to a customer, we've got to make it run fast. What we'll see next is how one can customize Joshua for an application to make a deliverable program. If we meter the hardware troubleshooter, we see that it attempts 1,000 or more unification merges in its reading network. Don't worry if you don't know what that is. It's just jargon for a certain part of the rule-finding stuff that determines which rules are ready to execute. However, of that 1,000, only 2% of those merges succeeded. Whenever a program attempts a large number of anything and only 2% work, that should wave a little red flag in your head that says some pretty serious efficiency gains can be had here. So here's the rule that drags the rest of the program down into the performance mire. It's a forward chaining rule called wire equality 1. It says that if you know the value at one end of a wire, and there's a wire from one point to another in the circuit, then you know the value at the other end of the wire. There are two problems with this. First, it thinks wires are directional devices. We need another such rule to tell us about propagating values along the wire in the reverse direction. It's as though every wire were a pair of cross diodes or a pair of one-way streets. The second problem is that it compares every value with every wire in the entire circuit and fails to match variables most of the time. That's where all the performance is going. It's using the wrong representation for a circuit because it doesn't have a good way of telling just what wires come off a given terminal of a device. Now, there are much better ways of modeling circuits. For example, a real circuit is a network of nodes connected by arcs that represent the wires. This is a more natural representation of a circuit than a collection of facts about voltages. In this case, the program can have its finger on all the wires going out of a certain point without having to examine every wire in the circuit. This process, changing the representation of data Joshua reasons about, is called modeling. The intuitive foundation of modeling is that sometimes the world tries really hard to tell you what data representation to use. Here, for example, representing the circuit as a directed graph seems like a pretty good idea. In other cases, you might want to use an SQL database, for example. The main advantage of Joshua is that it lets you make those choices without having to change any of the rules. The real strength of Joshua is that it's a generic AI tool, built on a set of user-redefinable functions called the protocol of inference. Joshua divides the work of writing an AI program into two pieces, the AI engineering part and the software engineering part. The AI engineer concerns himself with predicates and rules. He cares only about what they mean, not how they're stored. The software engineer concerns himself with data structures like discrimination nets, hash tables, and so on. He concerns himself with how they're stored and looked up, not what they mean. These can be two different people. They only need to talk to each other via the protocol of inference. Just as an aside, we can not only customize how facts get stored, but we can do similar things for how rules are stored, how they're compiled, how a TMS works, and lots of other stuff. It's all under your control. Thus, Joshua can work with several different formats of databases. You can even have several different ones at the same time, all in different formats. As long as you stick to the protocol of inference, your Joshua application program remains unchanged. Here's the bottom line of what data modeling can mean for your applications. Before modeling, the diagnosis took about 1/3 of a second and ran at about 120 rules per second. After modeling, however, it got 3.5 times faster, and the effective rule firing rate went up by the same factor. By using the Joshua supplied tools to figure out what your programs are doing, you get some strong hints about what models might speed up your program. After all, anytime you can get a factor of 3.5 in performance cheaply, you're winning. Now, the nicest thing of all about that example was that we not only got a factor of 3.5 better in performance, but the rules didn't have to change. The effort invested by the AI engineer in increasing the performance was zilch, because the software engineer obeyed the protocol of inference. Fine. Now, one thing a lot of people want to do is hook their expert systems up to conventional databases. After all, most companies keep their corporate valuables in a database, so any expert system that's going to be worth writing will probably have to go look in that database. We're going to see now an example of just that. A couple of years ago, somebody at MIT's AI laboratory bought a Heathkit weather station and put it out on the roof. Someone else decided, gee, it was a shame to see all that data not on the network, so he hooked the weather station up to the computer network. We decided it was a shame to see all that data disappear each day, so we hooked it up to Status, which is an object-oriented database product also from Symbolics. You can imagine your favorite database instead of Status if you want. The actual choice of database doesn't matter as far as Joshua goes. So what we've got is a database that records things like time, temperature, wind velocity, and wind direction as seen from Cambridge, Massachusetts. What we want is a Joshua program that predicts the weather from the database in real time. But there's a problem. A pile of numbers, like temperature as a function of time, is the wrong level of abstraction for an expert system to reason about. Instead, we want to summarize the data so that the expert system sees just an abstract representation. For example, it may want to know merely whether the barometric pressure is generally rising or falling, not every last fluctuation in the last 3 months. So we build a set of models that not only connects to the database and translates to and from Joshua's format, but also does smoothing, curve fitting, and the like. The Joshua weather predictor sits on top of that and deals only with the summaries of the weather data. You can, if you like, imagine your favorite time series analysis package between Joshua and the data. This is a backward chaining rule called Predict Dry Snow. It tries to figure out when it's appropriate to expect cold, dry snow in New England. Now, New England's weather is dominated by the ocean and by cold Canadian air, so we only have to check a few things. This rule says we should predict dry snow when the barometer is falling. Note here we've abstracted the contents of the database into just the symbol, rising, falling, or steady. The expert system doesn't need to deal with the full impact of the numbers in the database. Next, figure out the average barometric pressure over the last 2 hours and check that it's less than 1,000 millibars. Note the free mixture of Lisp. Joshua is so well integrated with the Symbolics Lisp environment, you think of Joshua as an extension to the Lisp environment, not another language. Then we get the average temperature and check that it's below 40. Finally, we get the average wind direction and check that it's more or less from the northwest. Thus, if the barometer is falling, it's below 1,000 millibars, the temperature is below 40, and the wind is from the northwest, then we should expect cold, dry snow. So let's try to get Joshua to predict the weather. Suppose I want to know what the Joshua weather predictor would have said about my trip to work yesterday morning. It says here the weather would have been rainy. Now I just happen to have here a clipping from the Boston Globe showing the weather prediction for yesterday. Note that Joshua and the weatherman both agree that it was going to rain yesterday morning. In fact, it's trivial to make Joshua look through the weather database for interesting weather in the near past. Here we'll look for interesting weather predictions at 3-hour intervals over the last month. It says here that it snowed in April. I remember that occasion because one of my colleagues was trying to go fishing during that snowstorm. I didn't say the weather was good, I just said it was predictable. Well, what you've just seen is an application that collects weather data in real time and then uses an expert system written in Joshua to reason about the weather data, generating short-term weather predictions. Joshua opens the door to getting AI programs to connect to literally any other program, so long as it has a program-callable interface of any kind. For example, one can write a Joshua program that asks about the performance of op-amps you've just designed. The way you'd express that in Joshua is to ask the frequency response of the op-amp. The way that might be implemented by the person who wrote the Joshua application would be to call SPICE, a large Fortran circuit simulator. In this case, the so-called database for this program is the set of all possible circuit simulations that SPICE can do. How's that for a big database? Flexibility and performance aren't the only advantages to Joshua, of course. One major advantage is what we call one-stop shopping. Symbolics can service your AI development and delivery needs in hardware, software, support, consulting, and education. You'd only have one phone number to remember instead of 5. Also, Joshua is quite affordable as such things go. Think, for example, of how Joshua can leverage the cost of your engineers. The main cost in application development, after all, isn't hardware and isn't software, it's people. And Joshua gives engineers the freedom to use their entire bag of tricks in the service of the customer. Here's the bottom line. Joshua is a high-performance, generic AI tool integrated with the list machine, it's affordable, and it's able to connect to almost anything. For more information, contact your Symbolics sales rep.